We're moving on. We're here in the PLC Professor Workshop where I develop my lab projects with the hardware that you see around me. We've been doing analog, and I apologize for how long those lectures were. It just goes on and on. There's just more information. Probably should have broken it into 4 sections instead of just 2, but it was still taking you just as long to watch it. So thank goodness for pause, right? Okay, our next lecture, the one we're going to do right now, we're going to start doing languages. And you know that with the RSLogix Studio5000 or the Logix engine, there are 4 languages you can program with. Obviously, ladder logic diagrams is the most popular, function block diagrams, structured text, and then sequential function charts. So we're going to start on those 4, and we're going to start with the most obvious, ladder logic diagrams. You're probably thinking, well, you know, we've been using ladder logic diagrams for many lab projects now. What we're going to do is we're just going to back completely out of the, I guess you'd say, the programming or the logical sense of it, and just focus really on ladder logic diagrams and how they function. And that's what this lecture is going to be. You had a lab project, so let's go and discuss your lab project. Ladder logic diagrams have been covered extensively in the first series of project manuals that we offered, the Complete PLC Learn series, which is based on RSLogix 500 and either SLC 500 or MicroLogix processors, or the 500 Emulate. So we have covered ladder logic diagrams extensively already before this presentation. So this presentation really is emphasizing some of the differences between MicroLogix SLC 500 realm and the realm of the Logix engine, which is supported by RSLogix 5000. We're not going to cover everything for ladder logic diagrams. When it comes to the other 3 languages, structured text, function block diagrams, and sequential function charts, we do go into great depth, but not on ladder logic diagrams. With ladder logic diagrams, there is no limit to the number of parallel branch levels. When they say no limit, they mean no practical limit. Obviously, there is a practical limit, what you can see on this screen comfortably, what you can troubleshoot with, in the amount of memory that you have in your processor. With 5000, you have some other approaches that you can take, especially for your outputs. So in this example, like you would use for 5 or 500, you put the output, the OTEs, in parallel to turn them all on together. With RSLogix 5000, if you have conditions or permissives that are of an OR logical nature, they have to be in parallel. There's no way around that. But the outputs that you want to turn on all at once, you have a little latitude. As you can see in this second rung of logic, that you have 4 groups of 8 in parallel. Now the reason for doing that is for visual expediency when you're troubleshooting. If all that you wanted to do was to turn on all of those bits, you could do it with a move instruction. I created a tag called all on, and if you make all 32 bits 1s, binary 1s, the decimal equivalent is -1. And then my destination is a double integer that I created called outputs_32. You can't have 32 in front because you can't start a tag name with a numerical character. But there is basically no limit to the number of parallel branch levels. However, the practical limitation is visual when you're actually troubleshooting, and when you're jumping rungs with the scroll bar, it goes from the head of one rung to the head of the next. It doesn't easily scroll down, and so you can actually lose your view of your conditions and your permissives while you're scrolling down trying to see if the output is in that branch. You can nest 7 levels deep, and this is true in almost any RSLogix platform. Now there are 7 levels there, but only 6 of them are nested. The top one that has permissive 1 and output A, that is not a nested level. That is the wrong. Starting 2, 3, 4, 5, 6, and 7, those are 6 nested branches. Now that is ugly. I would never write a rung of logic like that. With RSLogix 500, that is your limitation. However, the logical equivalent using RSLogix 5000 is the rung below. If 1 is true, then A is on. If 1 and 2 are true, then B is on. So if you compare the upper rung with the lower rung, you'll see that they logically are equivalent. But remember, these are not electrical circuits. If this were an electrical circuit, this wouldn't work. The upper one would, but the lower one would not, because you would have A, B, C, D, E, F, and G loads all in series, and they would have to split the voltage. It would just not work out. So it takes some getting used to what I call the sequential logic writing, putting everything in series, and it's just a logical statement. If 1 is true, then turn A on. If 1 is on and 2 is on, then turn B on, and so forth. Tag names, pointers, aliases, anything you want to call them. These tags right here represent the latitude that you have in creating tags in RSLogix 5000. The first one that I named bit, literally the name is bit, and it's a Boolean. That is the basic data type, or in RSLogix 5000 we have atomic data types, and I'm not going to go through all these in this presentation. We went through them in an earlier presentation that came with volume 1 of RS 5000. This is a video that will accompany volume 2 of RS 5000, more advanced subjects. So we've already covered the atomic data types. The bool or the Boolean is one of those. Word.21, we created a tag called word, and it's a double integer, so it's a double integer word. The members, if you would like, or the elements of word are 32 bits, 0 through 31. Now, I don't show all 32 here. And this one, everybody understands. If you create a double integer called monkey, you're going to have monkey.0, monkey.1, and so forth. These two tags right here, bit and word, are the ones you're probably the most familiar with. This is a user-defined data type. The data type is cylinder. And this instance of the data type cylinder we named insert part. The members of cylinder, as you can see there, are extend solenoid, retract solenoid, extend switch, retract switch. And of course the extend and retract solenoid, those would be tags that you would alias to actual outputs that control the dual valve, the double solenoid valve body for that controls that cylinder. Extend switch, retract switch would be alias to the proc switches, the Hall effect switches, whatever the switches are that tell you when the cylinder is fully extended and fully retracted. So this is another type of tag structure. You have members of a data type, so insert part, extend switch. This is yet another type. We have a single array called stack location. The tag name is stack location, and we made it's a single dimension array of 10 double integers. In this case, we are using stack, the third element of that array, stack 2, as source A for our equal instruction. And we're going to stick to the same data comparison through the rest of these tags. So that is an element of a single dimension array. This is an element of a two-dimension array. So floor location. The first one, stack location, we had a stack of 10 double integers. This could also be a stack of cartons or a stack of products, and we're looking in the stack to see if in location 2 it is equal to 3987. That would be like an ID for an object. So we looked in the stack in position 2 for 3987. In this one right here, we're looking in a two-dimensional array. We're looking at, and I say floor location, if you picture on the floor a 10 by 10 grid, we're looking in the coordinate 3, 7. So that would be 3 over and 7 up. We're looking in that location to see if it is 3987, 3987. So this is a tag that represents an element in a two-dimensional array. This is an element in a three-dimensional array. So we have 3 dimensions, 10 by 10 by 10. The previous one represented a 2-dimension, which would be 100 or 10 by 10 squares on the floor, or locations on the floor. And again, the first one was a stack. Now we kind of combine the two. We have 100 spaces on the floor, and each space has a stack 10 high. So it's 10 by 10 by 10, or we have 1,000 locations. And we call this a storage location, so you could picture it as a room that has 10 columns, 10 rows, and 10 stacks, 10 elements in the stack. And we're looking floor location 6, 5, stack location 8, 6, 5, 8, and we're looking to see if that is 3987. So that's another type of tag. This one is a little different. We call this sorted. This is a single element array, but it is a member of conveyor inventory. So picture, if you will, that we have a user-defined data type called conveyor. The class of objects is called conveyor inventory, and the name or the instance is sorted 1. So let's say we have 30 spurs coming off of a sorter, and as cartons come down the sorter, the barcode is read, or the virtual location has been recorded and followed by way of pulse generators down through the system, and when it gets to the sorter, it sorts out specific cartons. They don't all have to be the same, but they have to be meant for the same unit load onto a spur. So sorted 1 would be spur 1, and each of these positions would have a code in it that represents that carton. If this spur can allow 10 cartons on it before it's full, then we have 10 positions on the carton, and we're looking in position 4, which is really the 5th position. We're looking in position 4 to see if that is equal to 3987. So again, this is a member of an array. The data type is conveyor inventory. The name of this instance is sorted 1, and the member is position, and position is a 10 element single dimension array 0 through 9. And here we have something a little more complex. We have a user-defined data type called carton ID. So for a carton somewhere in the warehouse, that carton has product, it has quantity, and it has a production date. And this is a 3-dimensional array. So in a warehouse, when you think of floor space and height, you have columns of product that fill in a 2-dimensional array, which gives you 3 dimensions. So we have a 10 by 10 by 10. This is very similar to storage location. The major difference here is that storage location, which you see to the right there, 658, that's a 3-dimensional array. But in this case, this 3-dimensional array is made up of a data type called carton ID. So we're looking at a member of a 3-dimensional array, not the element, but we're looking at a member of the element of a 3-dimensional array. So these are this is some of the latitude that you have with RSLogix 5000 for tag name. The Logix engine evaluates instructions based on the run condition preceding the instruction. It is worth mentioning here that the highlight on these instructions, in other words the green highlight that is before and after the structure, this is not the run condition, although it is indicative of the run condition. Those green highlights represent the state of that bit in memory. The only exception would be the timer on delay instruction. The enable bit shows that the true or on if the rung is true at that point, And of course the done bit, that's a different story. Again, that represents a bit. The enable and the done bit are both represented here as their on state. So I would not ever use the highlight to describe the run condition, although the run condition in to display enable switch, which is false, the run condition in is true and the run condition out is false. Let's do a little more of that. Run condition in, run condition out. So you see the run condition in to the start push button, of course, is true because you're in the run mode. The run condition out of the start push button is true because that bit is on the memory. It's a true if on instruction. The run condition in to display enable switch is true, but the run condition out is false. So when they talk about run condition in and out, they're talking about whether or not the instruction is true or false. And again, the highlighted instructions are memory state, not run condition. Run condition in, run condition out. So you see display enable switch, that instruction is true because that bit is off. That's a true if off instruction. However, the run condition out of display enable switch is false because the run condition in is false, because the run condition out from the first instruction is false. I'm sure you're getting all this, even though it sounds like a mouthful. We're not going to show all the run condition in and outs for all these instructions, but you can see we have a run condition out from the on delay timer because it is enabled. The run condition in to the LED there is on, the run condition out is true, and so forth until you get to sequence done. Because the timer's not done, the run condition out is false. This is all very sophomoric, but when you look at this logic, will the bit LED_05 ever be on? Now I'll just let you think about that for a minute. If you look at the logic, under what conditions would the whole run be true? Even though sequence done bit is on and that instruction is true, would sequence.tt, sequence timer timing, would they both be true at the same time? So I've modified that wrong so LED_05 could come on. In the third rung there, it'll never come on because you're either timer timing or done, but you're not both. So I modified the rung to give you something slightly different. So here we have the timer timing bit is off, the run condition out is false, LED04 is off. Remember that output instructions are never true or false, they are on or off. Run condition and performance. Run condition and performance. Remember, run condition is the condition before and after each instruction. How does that affect performance? By performance we mean processing speed. You always want to start with the most likely to be false instruction. Between these two you have a start push button tag and a display enable switch tag. These are both inputs. If the display enable switch is not on, then this is true when we hit the start push button, regardless of that. One of these instructions is more likely to be false than the other. And of course, the timer timing bit and done bit are most likely going to be false if the timer is not enabled. If the timer is not enabled, then the timer timing bit is not going to be on, either is the done bit. Now, a caveat here is that the order of the logic, in this case, we don't want the timer enabled unless both of those conditions are true, the true if on and the true if off instruction. The point is that if the run condition is true, then it takes a little more execution time to execute the rest of the instructions. As soon as the run condition is false, then it actually executes a little faster. So you always want the instruction most likely to be false to be first in the rung. All instructions on a rung are executed regardless of the run condition in, but a false execution is faster than a true execution. So performance is optimized by placing the instructions in order of likely to be false. With a false instruction, the remaining instructions are executed with their run condition in set to false. Most instructions execute faster when their run condition in is false rather than true. Just a small detail. With the performance of today's processors across the board, speed is usually not an issue. Even memory space is not an issue. There are some very, very large projects, and of course, as engineers, we always like to get as much as we can get before we start giving up anything. So we go for the fastest execution. However, if putting the most likely to be false instruction first reduces the readability of the rung, I don't think I would do that. I tend to write all of my code in a way that is easy to read by whoever has to look at it fresh under the conditions and the pressure of the system not running. In other words, the maintenance personnel, whoever has to maintain the system. Really, I defer to their convenience for easy to read. So typically, I don't make an effort to make the most likely to be false instruction the first one. I write my logic so it's easy to read. But I wanted to mention that this is a way to improve performance if you really need to. Let's look at this rung. If I00, it's just a tag if_I00. So if I00 is true, branch start, then OTE output 00, next branch, so that would be an AND if. I01 is true, branch start, that implies an OR, then output 01, next branch. If I02 is true, then branch start, then output 02, next branch, output 03. And then you've got branch end, and branch end. That's a lot of instructions. How many instructions address memory locations? Now, there's some instructions that imply logic. They're logical instructions. But how many instructions actually address memory locations? Well, that's an easy count. 1, 2, 3, 4, 5, 6, 7. How many instructions are just for branching? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 instructions in this, if you want to call it rung, that are just for branching. Why not eliminate the branching? Now, we've already gone into this somewhat. I'm just emphasizing this feature of RSLogix 5000 and the Logix engine. So if we eliminate the branching, then we're left with just the instructions. And notice I did them in order of execution as far as actual logical examination of the bits. If I00 is on, then turn on output 0, and if I01, then output 1, and if I02, then output 2, and also turn on output 3. What would the rung look like? If I00, then O00, and if I01, then O01, and if I02, then O02 and O03. So here we have just the instructions that actually address memory location. Much simpler. And it is equivalent logically. It's quicker to write, quicker to read, takes less memory, and less execution time. Now, some may want to argue the easier to read. When I first saw this style, this capability of the Logix engine, RSLogix 5000, I literally said to myself, oh my goodness, somebody's going to do this, because I didn't like it. Then because I was teaching it, I needed to include it. Once I started writing labs using this style, it dawned on me how much simpler and how much better this was. Once you adapt, rid of all the emotional baggage of relay contacts and coils, and you just think logical expression, believe me, you're going to like this much better. So here's our two rungs. I express them both in, we'll call it, it's not really structured text, but it's similar to structured text. XIC, if I00, BST, OTE, etc., etc. So you can see how much shorter it is even just to type it in, because you've eliminated the BST and the NXBs and the BNDs. And of course, these are not electrical circuits. I don't think of them as electrical circuits anymore. I've not in any way thought of this as an electrical circuit in many, many years. And if you're just learning ladder logic and you did not watch any of the earlier videos, especially the Complete PLC Learn series that is based on RSLogix 500, then you're at a disadvantage. If you get to the same place in the end, I guess it doesn't matter. If you're writing code, it's working well, your boss is happy, you're getting paid, mom is happy, everybody's happy, well then that's great. However, anything that you skip over between the very first lecture that was provided for the Complete PLC Learn series and the lecture series, any little detail that you've skipped over and you've not accumulated does create a weak place in your ability to analyze problems and outsmart them. So I would advise you, if you have not watched the earlier videos, to go back and watch them. It is analogous to being able to do math longhand but using a calculator instead, as opposed to you never learn how to do long division and square roots on pencil and paper, but you can do it on a calculator. Then you really don't understand what you're doing. You get the same result, but you are a little short on tools when it comes to real serious analysis when you're troubleshooting. But if it works for you, I don't mean that as criticism if you didn't learn all the little details along the way. Thank you for watching this presentation. This was on ladder logic diagrams, and it was in the group called Languages of the Logix Engine. This particular presentation is a standalone that is not really covering any lab projects. It's just pointing out some of the differences between 500 and 5000 for using ladder logic diagrams. The other three presentations that are similar to this, specifically for function block diagrams, structured text, and sequential function charts, those are included with lab projects from the manual. This was a sort of odd man out lecture that I threw in just to cover ladder logic diagrams to make it a complete set of videos. Thank you for watching.